If you've spent some time with differential equations, you probably know they can be difficult to solve, and sometimes even impossible. Thankfully, we don't always require an exact solution, and in many cases, an approximate solution is good enough. One of the simplest ways to approximate a solution is by using Euler's method. However, if you just read the formula for Euler's method, it is not exactly clear what is happening, or why it even works. So in this video, we are going to get a better understanding of Euler's method, by first coming up with an intuitive way to approximate solutions to differential equations, then see how that translates into Euler's method, and then finally test it out on a real-world example. Since we are just starting off, we are going to use a very simple differential equation, dy dx equals y. So this means we are looking for a function that is its own derivative. Many of you probably already know the solution to this differential equation, but pretend for a second that you don't. Imagine if you were given this and asked to find an approximate solution to it. After some thinking, one thing you might recall is that the derivative can be thought of as the slope of the function at a point. We don't know what our function should look like, but using our differential equation, we can see what its slope would be if it passed through a certain point. So, if our function went through the point 1, 1, our differential equation tells us that it would need to have a slope of 1. We can visualize this by putting a tiny line there with an appropriate slope. This shows how the function might look if it passed through this point. Similarly, if it went through the point 1, 2, it would have a slope of 2. We can repeat this for all points on the grid. This starts to give us an idea of what our solution might look like. You might even be able to use this to draw an approximation of what the solution might be. But rather than finding a solution by eye, let's see if we can come up with a more systematic way. We will start at an initial condition. An initial condition is basically just a point that our function needs to go through. Otherwise, there might be an infinite number of solutions to our differential equation. An initial condition helps us narrow it down to just one function. Usually, the initial condition is given by the system we are analyzing. For this question, I will pick the initial condition to be y of 0 equals 1. This means that our function needs to go through the point 0, 1. So, starting at 0, 1, I know that the slope there is 1. So the function will be following the line. Since we are trying to find an approximate solution, we can assume that for a little bit, our function is going to follow this straight line. But a real solution might be curvy and not follow this straight line. So why can we assume this? Well, looking at any smooth function, you might realize that if you zoom in far enough, it appears to just be a straight line. The more you zoom in, the more it looks like a line. Back to our example. Let's say that it is linear for 0.25 units. Now, we have an approximation for our solution for this short segment. We are now at 0.25, 1.25. Using our differential equation, or the slope field, we can see that here the function should have a slope of 1.25. We can continue this for our next point, and then the next, and then so on. This gives us a pretty nice approximation. But we can improve this. For this approximation, we assume that our function was approximately linear for 0.25 units. This increment of 0.25 units is known as the step size. If we choose a smaller step size, like 0.1 or 0.01, we'll have to calculate the slope more frequently, which makes our approximation more closely follow the actual curve of the solution. However, there is a trade-off. A smaller step size does provide a more accurate result, but it also requires more computation, whether that is done by hand or by a computer. So, it is important that you find a step size that isn't so large that the approximated solution is inaccurate, but also not too small that it will take too long to compute. Now that we have an intuition for why Euler's method works, let's see if we can formalize it. I want to preface this part by saying that you do not need this to use Euler's method. To see a real-world example of using Euler's method, feel free to jump ahead to the next section. I'm including this because a lot of you might have learned Euler's method this way, and I want to connect it to what we just did. Also, this is quite helpful if you are trying to get a computer to estimate the solution. To get the formula, we're going to introduce some notation. We will be working with x and y, but keep in mind that sometimes you'll find that t and y are used instead. We will define f of xy to be the slope at a point xy, which will come directly from our differential equation, and we will denote the step size with h. Given that we have starting conditions x0 and y0, we will see what our next point should be. The x-coordinate of our next point, x1, will just be x0 plus our step size, which is h. The y-coordinate, y1, will just be the starting condition y0 plus the slope at x0, y0 times the step size. And now we can write this more generally by recognizing the pattern will continue. So we get that xn plus 1 is xn plus h, and that yn plus 1 is yn plus h times f of xn yn. If this looks a little daunting, don't worry. As I mentioned previously, this is not required to actually use Euler's method by hand. Let's see how Euler's method can be used with an example of a rocket. We will be looking at a simplified model of a rocket. The forces on the rocket are the force of thrust pointing upward, the force of gravity pointing downward, and the force of drag also pointing down. All of these equal the derivative of momentum. Momentum is just mass times velocity. Keep in mind that both mass and velocity are changing with respect to time, so we will have to use the product rule. To simplify the problem, we are going to assume that the rate at which the mass of the rocket changes is constant. So we will replace that with the variable mr. Now, to isolate the derivative of a velocity, we can subtract velocity times the change of rate of the mass, and then we can divide both sides by the mass of the rocket. The mass of the rocket at some point will equal the initial mass plus the rate of change of the mass times time. We know that at the start, our rocket is stationary, so at time t equals 0, the velocity is 0. Now, we are going to use Euler's method to estimate a solution. I have added the actual solution in the background to see how accurate our estimation will be. When I'm doing Euler's method by hand, I find it helpful to make a table like this so I can keep track of all the numbers. Here are the values to all the variables we are going to be using, if you would like to follow along. We will be using a step size of 0.5 seconds. So now we can start to fill in the time values. Now, using the initial condition, we can get the slope at 0, 0. Going through the calculations, you would find that this equals 20.2. So we can multiply that by our step size of 0.5 and then add it to the previous value. Now, we need to find the slope at 0.5, 10.1, which is approximately 19.43. We can multiply that by 0.5 and then add it to the previous y value, which was 10.1. Now, let's do one more step before we have the computer do the rest of it for us. We need to find the slope at 1, 19.81, which turns out to be 16.74. Like we did previously, we multiply this by our step size and then add it to our previous value to get 28.18. Here are the rest of the values. As you can see, it does a pretty good job of hugging the real solution. As mentioned previously, decreasing the step size will give us a more accurate result, but keep in mind it does increase computation. So, as you can see, Euler's method can be quite useful in estimating solutions to differential equations. I also want to mention that there are many other ways to estimate solutions. One of the most popular ones is Runge-Kutta, which is actually what I used to find the solution in the previous example. However, usually this method is not done by hand, but by computers. I hope that you found this video useful. Thank you for watching.